Welcome back to our introductory course on data visualization. In this class, we are going to study methods that allow us to visualize associations among variables, such as scatter plots and heat maps. One important thing for us is that we can organize the many visualization tools in different ways. If you search the literature, you're going to find various forms or various ways of organizing the many graphs and the many data visualization tools. The way that we chose to do here was based on either what you can observe from the data or what are the relationships that you can find from the data and within the data. So the organization that we did here was on distribution, associations, amounts, proportions, evolution and flow, and geospatial. Let's go quickly into each one of these. So data distribution here, I am basically referring to visuals that allow us to see how one specific variable is distributed in the space. Right? And to do so, we can use the histogram or the box plot or the violin plot. These are the three ones that we are going to review here. Then we are also going to talk about the associations. In this case, we want to investigate the association between two variables, and we'll have the scatter plot matrix, heat maps, and the bubble chart. Here in the amounts, we are going to talk about the bar chart and the radar chart for numeric data. When we talk about the special types of data, we are going to talk about the word clouds. The other types of special data, like time series, trees, and graphs, we are going to see in another topic as well. Well, proportions, as the name implies, is when you're going to use a visual or a graph, and this visual is going to be divided into parts, and each part is going to represent a proportion of one specific variable. In this case, we are going to study pie charts, tree maps, the donut chart, and sunburst and dendrogram we are going to see in a different class. We are not going to see them in this class. And then we have evolution and flow. In this case, we are going to study the Sankey chart and the Gantt chart. And finally, geospatial data, we are going to see the choropleth map and the bubble map. Well, so let's go into the distributions now and start discussing these three types of visuals to plot data distributions: the histogram, the box plot, and the violin plot. I am initially to give you a brief presentation, a brief conceptual presentation of each one of them, and then I'm going to illustrate with one or more examples of what are these graphs and how they are used and what we can interpret from them. In the case of the histogram, it's usually used to explore and visualize the distribution of a variable, and it's used for continuous data. And this is something very important. We need to know what type of visual is adequate for each type of data that we have. If I have a variable that is not continuous, then I cannot use a histogram. If I want, for example, to visualize the distribution of a variable that is a discrete variable, I will have to use a different type of chart, for example, a bar chart. But if the variable is continuous, then I can use the histogram. And the idea of the histogram is very simple. It basically divides the range of a given variable into different bins or sub-ranges, and it counts the frequency of occurrence of objects within each of the bins that have been used to divide the whole range of the variable. So let's have a look at it. In this case, I'm simply plotting a random distribution here, and here I am plotting the variable temp for the forest fires data set. In this distribution, what we can observe is that I am dividing the variable into bins of equal width, and I am counting the number of objects that I have within each bin. Right, so here I have approximately 200 objects in this bin. Then in the second bin that goes from here to here, I have approximately 165, I would say, and so on and so forth. As I mentioned before, we can observe here that this distribution shown by the histogram, it allows us, for example, to observe that this variable, it has a tail to the right that we call a positive skew. And if the variable has a positive skew, it means that I have some outliers here. The longer the tail, the more distant is my outlier from most of my distribution. So this visual allows us to find the outliers in the data. And it also allows us to observe the trend. What we can see is that as the value of the variable increases, this value here on the y-axis decreases. Another thing that is very important that we can observe here is when we plot, for example, the median and we plot the mean, we can see that the mean is greater than the median. When the mean is greater than the median, this is an indication that we have outliers to the right, because the mean is sensitive to outliers, whilst the median is not. And the way that the mean is calculated is by summing all values of the variable and dividing by the number of values, whilst the mean, I simply order the values of the variable and take the value in the middle. Or I take both values in the middle of the distribution. If I have an even number of values, I sum them and divide by 2. That's how we calculate the median. Okay, so as we discard the extremes in the median, so it's much less sensitive to outliers than the mean. And in this distribution here, we have also bins of same width plot in this histogram. And what we can see is that this distribution has a shape which is very similar to a normal distribution. As I mentioned, this is the variable temperature for the forest fires dataset. Another thing that I can observe here is the fact that I have a small plateau, almost a hill here, and this represents what we call a mode, right? So this is the main mode of the distribution. In this case, the mode corresponds to the maximal value, and here I've got a small mode, which is a sort of local optimum of this distribution or local maximum of this distribution. And this can also be observed by visualizing the histogram or visualizing the distribution of this variable. So this way we can see the importance of visualizing the data. We are very used to apply the learning algorithms into the data, but sometimes we can have a lot of information and we can have a lot of conclusions by simply visualizing the data and the variables. Talking about the box plot is a different way of looking at the distribution of a variable, and it's based on the printing, or it's based on plotting a box with the distribution of your data set. It's based on plotting a graph that contains basically the minimum value of the variable, the maximal value of the variable, and what we call the quartiles, which are the division of the values of the variable into 4 parts, each part separated by one of the quartiles. Right? So when you take all the values of a variable, you order them, you divide them into 4 parts, you have the quartiles dividing each of the 4 parts. We'll see that in the following slide. And this is called the 5-number summary of the variable. Okay? It's also used for continuous data, and its interpretation is based on the general shape of the box plot, also called box and whisker plot. So let's have a look at the box and whisker plot. Here I have a normal distribution randomly generated. As we can see, it is almost a perfect normal distribution with its peak a little more to the right here. And here on the left, we have the box plot for this distribution. What we can see is the minimal value, excluding what has been identified as the outliers. And this dashed line here, they are separating what has been defined as outliers from the left side and from the right side of the distribution. So the value here is approximately minus 2.8 or 2.9. It's very close to minus 3, and also minus 3.2 or minus 3.3 here. These values are plotted here, and they are considered outliers. And it's interesting to observe that most tools that we use, it can be Excel, it can be any function or any method, for example, in Python or in R, they will generate these outliers. They will calculate these outliers automatically for us, right? And the way that they do it is by using an empirical rule that takes into account the range within the box, which is called the interquartile range. The interquartile range is the difference between Q1 and Q3. And as I mentioned before, you get Q1 by ordering this variable from its smallest value to its largest value, and you take 25% of the objects, they compose Q1, the other 25% compose Q2. Actually, Q2 is composed of all the data that are from here, from the minimal to Q2 to the median. And then we have Q3 contains 75% of the objects. And we have here, if you take the whole box and whisker plot, it contains, of course, 100% of the objects, of the values of the variable. So this is one representation of the distribution using the histogram. This is another representation using the box plot. Let's now talk a little bit about how can we use the box plot to detect outliers. I mentioned in the previous slide that we have an empirical rule that takes into account the interquartile range. And basically what this technique does is it takes the value of Q1 and the value of Q3, and based on them and a predefined multiple or constant, we calculate if a value belongs to this range or not. Right? So values greater than Q3 plus gamma times IQR or smaller than Q1 minus gamma times IQR are considered outliers. Usually, what most packages use is gamma equals to 1.5. So this means that any value that is greater than Q3 plus 1.5 times the interquartile range are considered outliers. And any value that is less than Q1 minus 1.5 times the interquartile range is considered an outlier. All right, so let's make a parallel between the histograms that we've seen before with the box plots. So here we have the corresponding box plot for this histogram. And it's very interesting to observe the shape of the box plot here, because what we notice that we have a high concentration of objects within the box occupying a small range of values. And remember that the box itself contains 50% of the objects. So 50% of the objects are within this box, and the rest is spread from here to top and from here to bottom. What this shows us is that we have a high number of outliers. This is caused by the tails. So we have a long tail here, and we also have a long tail to the right. So the tail to the right comes here on the top of the box plot, and the tail to the left comes here in the bottom of the box plot. If we have a look at a uniform distribution like this one, what we see is that we have a much bigger box, and we don't have outliers. And the reason why we don't have outliers is because we don't have tails. So we can conclude that uniform distributions have no tails. As they have no tail, we don't have outliers appearing here in the box plot. What if we change a little bit those distributions? For example, in this case, we are transforming the normal distribution. We are making it more peaked. So we have a higher peak, and we have even longer tails. And the normal distribution, I'm now transforming it into a sort of semicircle. Now, I still don't have tails, right? But it decreases in terms of count for smaller values and for greater values in the x-axis. And what happens is that the box plot now has a huge number of outliers shown here, and this is an outcome of the tails that we have in this more peaked distribution. For the semicircle, we also have no tails, so we basically have no outlier because the behavior is very smooth of this distribution, and its shape is very symmetrical around its median that is plotted here in orange. What if we have highly skewed distributions? This is a right skewed distribution. This is a left skewed distribution. In this case, what we observe is that if we have a right skewed distribution, this means that we have a lot of outliers around the greatest values of the variable, and the left skewed distribution, we have the opposite case. We have a lot of outliers on the left-hand side of the distribution. Finally, to conclude the distributions set of visuals, we have the violin plot. The violin plot can be understood as an extension of the box plot that is capable of showing us the density of data within the distribution, right? Which is something that we don't see because in the box plot, because when we plot the box plot, we basically see the mean, the max, the box, and the outliers, but we don't have any information about where we have a higher concentration of objects. So the violin plot also works with continuous data. And as I mentioned, wider areas are going to represent regions with a larger density of data points. And these are examples of the violin plots for these distributions. So this is approximately normal with a slightly higher concentration of objects around these values. And this is reflected here in this violin plot, right? So we can see this is molehill that represents this higher concentration, which means a higher density of objects around this area of my distribution. Then we have the uniform distribution. It's uniform, but we can also see that some bumps here, they represent the bumps that we also see in the histogram. And in this case, we have a normal distribution, but a very peaked normal distribution. And this also is represented in the violin plot here on the right-hand side. In the case of the semicircle, this is similar to the previous one. In this case, I'm making the comparison mainly with the uniform distribution. What happens there is that the density is represented here in the violin plot, which is what we are observing here. In the case of the right skewed distribution, this is also reflected here in the violin plot, and the left skewed distribution is also reflected here in the violin plot. And now I'm making a trade-off, a comparison, a direct comparison between the box plots and the violin plots for the variables for the species, the plant species Setosa, versicolor, and virginica of the iris data set of Fisher. And I also plot the number of objects and the objects here over the picture so that we can, for example, note that we have a higher concentration of data points here, causing the presence of these sort of bellies here in the violin plot. Thank you for watching and see you in our next class.